In this video, we're going to discuss Einstein solids. Einstein solids are an oversimplified model of a solid material. The basic idea is that we set up identical atoms next to each other, and each of the atoms has evenly spaced energy levels, so that the difference between any two energy levels is some constant value. And the idea is that each atom can be in some distinct energy level, and if we add up the energy level of each atom, we get the total energy of our system. So for example, we could set this lowest energy to 0 electron volts. We could say, okay, any atom that is in the lowest energy level has an energy of 0 electron volts, and then we could say that this is, say, 13 electron volts, and this is 26 electron volts. So in this sample Einstein solid, the jump between energy levels is 13 electron volts per energy level. This energy gap here corresponds to the frequency of oscillation of the actual oscillators. So this energy gap is always equal to HF, where H is Planck's constant and F is the frequency of oscillation. So in this case, one time HF is 13 electron volts. So I can either be in the ground state 0, or I can be at 13 electron volts, or 26 electron volts, or another 13 is 39 electron volts, right? So I'm only allowed to add function or factors of HF onto the energy of each of my oscillators. Now, I can distribute a given amount of energy throughout these atoms, and what we're interested in is how many ways are there of distributing a set amount of energy throughout a set number of atoms. And we want to know the multiplicity of this, right? How many ways can we reorganize it? So what we do is we count basically how many HFs of energy we have in total, and we call that the Q. So Q is the number of units of energy that we have. It's not the actual value of the total energy, it's the number of discrete energy units. So in this case, I have 2 in this oscillator, 0 here because I'm in the ground state, and 1 here. So I have 3 units of energy, and I have 3 oscillators. So Q is the number of units of energy, N is the number of oscillators, and what I want to do is I want to be able to figure out how many ways can I rearrange 3 units of energy between these 3 oscillators. So this is one way of doing it. I'm just going to draw the atoms as simple boxes here, just to save myself some time. Another way of doing it would be I could put this, all 3 units of energy into the first oscillator, and then I could have 0 units of energy in the second, right? So this would look like this oscillator here is in the ground state 1, 2, 3, and then this one is in the ground state, and this one is in the ground state as well. In order to be able to calculate how many ways we can rearrange this much energy with a set number of oscillators, is that we actually create a system where we have lines which divide the oscillators up. So the idea is that the space to the left of the first line, the space to the right of the last line, and all of the spaces in between the lines are oscillators. So I have 1 oscillator here, 1 oscillator here, and if I want to only have 3 oscillators, this is how I would draw it. I have 1, 2, 3 oscillators. And then I can put dots, which represent the energy, in between the lines. So here, this oscillator has 2 units of energy, so I put 2 dots. This oscillator has 0 units of energy, so I don't put any dots. And this oscillator has 1 unit of energy, So it put 1 dot. And now the problem of figuring out the total multiplicity of this system with 3 dots of energy units and 2 bars representing the spaces between my 3 oscillators is simply how many ways can I rearrange 3 dots, which are indistinguishable, with 2 lines, which are also indistinguishable. And as we found before, this is going to be 5 factorial, right? The number of total items divided by the number of ways of rearranging the dots, which is 3 factorial, and the number of ways of rearranging the lines, which is 2 factorial. So my total multiplicity, which I will call omega, is equal to 5 factorial divided by 3 factorial divided by 2 factorial. In general, we can write this as the number of atoms plus the energy, number of units of energy minus 1, right? So the number of atoms ends up, there's 1 less bar than there is number of atoms. So really my bars, so my number of bars is equal to n minus 1, and my number of dots is equal to q. And in total I have n minus 1 bars plus q dots. That's the total number of things that I have. I factorial that. So in this case, that's 5 factorial. And then I divide it by n minus 1 factorial, because I have n minus 1 bars, and q factorial. Now what I'd like to do is think about 2 Einstein solids next to one another, which can exchange energy back and forth. So what I would like to do is I would like to figure out what the most likely state of this system is, and there is a specific meaning that I have to most likely. And to get to that, we need to think about macro states and micro states. So the macro state is the number of energy units in each of these 2. We assume that they can't change numbers. That is, that this one has 7 oscillators, 7 atoms in it, and this one has 5 atoms in it. But I would like to know the most likely distribution of Q in between. And what I mean by this is, imagine that I'm able to kind of like shake the system, and the energy moves around randomly within the system, and then I open the bag after shaking it, and I look and I see what is the energy, right? And say I repeat that process 1,000,000 times. What state will I find the most often, right? What would be the most likely state for me to find after that shaking? Okay, so to get to that, we need to distinguish between 2 things. What I am interested in is the most likely macro state. The macro state is the state of the system where all I care about is the energy value that each of these 2 oscillators has. So for example, the Q1 equals 5 and Q2 equals 2, that is a macro state. I don't care how those 5 units of energy are oriented, distributed within the 7 oscillators within my first solid. And I don't care how these 2 units are distributed in solid 2. I only care that there's 2 over here and 5 over there. This is a macro state. So the idea is that the macro state describes the big picture quantities of a system, while the micro state describes the individual position of every unit of energy within the system. So for example, a micro state for N1, where it has 5 units of energy, is given here. My first atom has 2 units, so then the bars are in between. So I have 2 units, 0 units, 0 units, 1 unit, 2 units, and then I have 2 atoms without any. So I have 7 total atoms with 5 units of energy distributed between them. I just picked a microstate at random for that. I could have distributed the energy in many, many different ways, right? But that is one example of a microstate. The number of total microstates in this macrostate is a huge number, which we'll calculate. So in general, we're not going to want to write out every possible microstate because it would take forever. But that's an example of one. And for N2, I also have a microstate here where the first atom has a unit of energy, 4 atoms have no units of energy, and then the last atom has a unit of energy. So what we are going to do is we're going to try to figure out how many microstates are associated with each macrostate. Now let's actually calculate the number of microstates in several of the macrostates. I have not calculated all of them, but at least we have a few. The equation that we're going to use for the multiplicity, or the number of microstates in each of the solids individually, is our equation for the number of microstates, or the multiplicity of an Einstein solid here. And we are going to find the total number of microstates by simply multiplying the number of microstates in each of the solids together. To make sense of this, just imagine, for example, in this row here, my number of microstates in the first Einstein solid is 7. If I choose, so I have 7 options here, I choose one of those, and for each of those options, there are 210 microstates in omega, or in the solid number 2, that I could choose from, right? So each of my choices that I make here has an associated 210 microstates with it. So I have 7 times 210 is 1,470 total possible microstates between these two solids. Okay, so looking through the first row, using my equation down here, there is only one possible microstate of the first Einstein solid in which it has 0 energy. There's only one way to distribute absolutely no energy between 7 objects, which is for them all to have no energy. That's only one. Note that 0 factorial is actually just 1, so there's not a 0 actually in the denominator here. I then do the same thing here, and I find 330 microstates for a total of 330 times 1 is 330 microstates here. Now, as I continue to add energy to my first Einstein solid, as Q1 increases, my total number of microstates increases. Granted, the number of microstates in Einstein solid number 2 decreases because I have less energy to spread around, so fewer ways of spreading around less energy. But the multiplicity, the number of microstates in my Einstein solid number 1, increases faster, especially in the beginning here. So here I've dropped about maybe to 2/3 of my previous number of microstates when I move from 7 to 6 units of energy. But here I have 7 times more microstates in the Einstein solid number 1. So in total, I increase my multiplicity by a lot because I've dropped by about 30% here, but I've grown by 700% here. And this trend continues until I get to this line here with 4 and 3 units of energy respectively in Einstein solid 1 and 2. This is the most likely microstate, or sorry, this is the most likely macrostate of my system because it has the most microstates. And it doesn't have the most by a ton, but if you take, for example, these three together have close to 20,000 individual microstates, whereas these three together have maybe 5,000 microstates, right? So if I were to repeatedly shake the bag over and over and over again, right, if I mix up my energy in these Einstein solids, I'm about 4 times more likely to find the system in one of these 3 states than I am to find it in one of these 3 states. And in fact, I'm exceedingly unlikely to find it in this state. What we're going to find as we look at large numbers of particles in each of the Einstein solids and large amounts of energy is that these macro states, which have the largest number of microstates, will become exceptionally favored over the other states. That is, if we had, say, 10 to the 23 atoms and 10 to the 23 units of energy to spread between them in two different Einstein solids, we would find that it is incredibly likely that we would find the system in the most likely microstate or macro state. Finally, I'd just like to note a feature here that the most likely macro state is the one in which the energy is distributed approximately evenly with the number of particles. That is, N1 has slightly more particles than N2, so Q1 should be slightly larger than Q2. If I have more particles, I should have more energy with those particles. In general, the most likely macro states will be the ones where the energy density of the two Einstein solids is about the same.